Hi, this is Rishikant Mishra and this is my demonstration for the challenge 1. I'll be working alone for this challenge and I would just like to start with a brief overview of what we need to do for challenge 1. So basically we need to erase, program and verify 128 KB of flash main memory, and we need to also kick in the watchdog timer in this, which should be able to reset the system every 1 second if my code does not acknowledge the reset. Also, I need to set in a button, a forceful button, which will force the watchdog timer to timeout, and this all will be indicated by a red LED which will go on for 1 second. So a program flow will be this. Let's say this is a timeline. So a program will start with the red LED going on for 1 second, and as soon as that ends, the erase, write and verify program will begin, and the watchdog timer will also start at this point of time. So we need to keep resetting the watchdog timer and at the same time erase, program and verify the data that for 128 KB. Also, as soon as this process ends, we need to put in a green LED that should go on for about 1 second, and this whole process should take preferably less than 1 minute. And even if it takes less than 1 minute, the rest of the time over here can be idle, and as soon as 1 minute is over, we need to go back at this position and restart the procedure again. So basically this is our overflow, and let's discuss the code for this. So this is me. I hope that is clear. Yeah, let's discuss the code in the next section. So let's look at the code that we have written for this challenge given our objectives. The only thing that I wanted to point out is whenever I was creating a new project, my driver library was not getting well defined. So what I basically done is just copied the code and put it into a previous project that I have done, which is the blink LED over here, and which had a well set up driver library. So that's the only thing that I've done here. So let's look at the main code. So the first thing that we do is include the required headers and libraries, and we are using the flash memory API over here, so we need to include this driver library over here. Apart from that, everything is basic C code as required by the challenge. Then we define a subroutine, which is basically the erase, program, verify, flash, which takes the variable input as an integer. We'll discuss this subroutine at the end or in between the main program. Let's move on for now. So first we define an array containing the names of the memory sectors. The logic behind we need to erase and program 128 KB of flash memory. So we know that each sector in the flash memory contains 4 kilobytes of data. So given that logic, we need to erase and program 32 sectors, which gives us this. I'll just remove this makes more sense. And so that is the logic behind using 32 sectors. So 0 to 31, that makes it 32. And we define the starting addresses for each of these sectors. This is just a random start that we can give, and it depends on the user. So each sector will contain 4096 memory locations, which is nothing but, let's say, 20000 to 20FFF, and the next sector will start from 21000. So that's the basic logic. Each starting address will go up till 4 kilobytes of data. Then we initialize all the input output ports in this function. We'll call this function within the main program. So what we do is set our p1.0 as an output, p2.1 as an output, and p2.2 as an output, which are nothing but the red, green and blue LEDs. And this is something that is out of the scope of this objective, but this makes, I'll explain the code later on, but lighting the blue LED to indicate end of 1 minute makes the challenge look a bit more accomplished. Now what we do over here is create the hardware interrupt. We define the p1.4 direction as the complement of it. So when the button is pressed, the state will be 0, and when the button is not pressed, the state will be 1. It's a simple logic that we use later on. I'll explain it again. And we also enable the pull-up resistor on P1.4, and this is done just to remove the switch debounce that occurs, and this will make our program run smoother. Then we set the flash wait state to 2 for each of the bands, and initially we switch off the LEDs by using these functions over here. That is, the output is nothing but the complement of this bit. So this is our initialization of the input output ports, and we'll call this function later in the main program. Then we create a function. We initialize the function, not create. Initialize a function which will just create a delay for 1 second. And since we are not using any timer APIs or any system picks, so we'll be using the basic default frequency for the board, that is nothing but 1.5 megahertz. And as discussed in the blinky LED Watchdog timer code that we discussed in class, the count comes out to be this much. So basically that is what I've done. This creates a 1 second delay loop, and we have defined another function to create a 200 millisecond delay, which is nothing but 1 second by 5. So this count is divided by 5 over here. That's the basic logic over here. So now let's move on to our main function. I have created 3 counters, 1 counter for the sector counter, 1 counter for the delay, and 1 counter for the LEDs. You can also work with just 1 counter by initializing the counter whenever we need, but this is something that I prefer doing. It makes me know which counter I'm using for which application. Well, as I said, we can also remove any 2 and just work with 1 by initializing it every time. And then we call this function that we discussed earlier to initialize the input output pins and switch off all the LEDs for now. At first, then we move on, and at first we'll hold the Watchdog timer and we'll call it off after we indicate the start of the program, which is nothing but indicated by 1 second of lighting of the red LED, which is shown over here. So we light it up, we switch it on, we wait for 1 second, and then we switch it off. That is the simple program over here. Now this function over here is the main function that we need to use a lot of times, which is nothing but used to start or reset the Watchdog timer. So we know that by this we know that the Watchdog timer has a timeout of 1 second, like I said over here, 1 second. This is the code for that. So we need to acknowledge the Watchdog timer before 1 second, each 1 second that the program is running, so that we'll do multiple times in the program that I'll discuss later on. So this function is nothing but to start or reset the Watchdog timer. So at first we start the Watchdog timer at, let's say, as soon as the red LED is switched off. Then we go into our main loop, which is nothing but while 1, which is nothing but an infinite loop. So till the hardware reset, that is nothing but our P1.4 is pressed, this loop will keep on executing. And so first we initialize our counters to 0 again, just for safety measures, and then we enter this loop over here, which has a count of 32. So that means now we are into our main function, that is erase, program, and verify the flash memory locations. And since we need to do it for 32 sectors, we are using the count as 32. So from 0 to 31, that's the basic logic over here. And as I again said over here, we are using the same function over here to restart the Watchdog timer, just in case we don't want to trigger it and reset our program, so we'll be calling it multiple times over here. Then we call the main subroutine over here, which is nothing but erase, program, and verify flash, and this takes in the argument as count, which is set to 0 over here. So at first the count is set to 0, and we'll see what this subroutine does. So let's move down to the bottom. So right now our variable that we have put in is the sector. So right now our count is 0, so this is 0. So we are right now working on sector 0. That's the basic logic over here. Now we move into this, and at first we just initialize the buffer. Buffer is nothing but how much data we need to work on, which is nothing but 4 KB given our start location. So we initialize a buffer to a pattern of 0x00. We use this function, this API over here, memset, and this will start from this memory location, create a pattern of 0x00 for 4 kilobytes of data. Now there is a reason why we are using 0x00 pattern. We could have used any other pattern, but using this pattern makes it easy to verify data over here. As you can see, this flash 0 pattern we'll discuss when we come to this function, but there's a reason behind using this. So to work on any sector, first we need to unprotect the sector, which is nothing but using this API. So unprotect the flash main memory space 1 mem sector, which is not sector right now, is 0. Then using this API we erase the flash sector given by the memory address of this sector over here. So right now it starts erasing data for 4096 memory locations starting at sector 0. That's a simple logic over here. So with this function our first sector will be erased completely, and over here by erasing we mean setting all the memory locations to the default erase pattern, that is FFFF for all. We'll see that later on in the last section when we go to the memory browser and see what is happening within the board. And this is put into a while loop. Well, this while loop is a redundant loop. Basically it means that until and unless this process is going on you can continue, but if there is some error, that is this condition is not being met, we come out of the loop and the program stops, which is not going to happen, but still for this is good programming and we put it into a redundant while loop. Then we move on to the so right now our first sector at this point of time will be erased. Then we need to verify if that memory location in the sector, each memory location in the sector has been cleared or not. We do that by using this API, and it basically starts from this address, whatever address that we have set up, and it uses the flash 1 pattern default API default function to verify that each memory location has been set to 0FFFF. So that is what this one does, and again it's in a redundant while loop. If this condition is being set, there's no issue, but if there is some error in this function, we come out and the program stops. And after that we program the sector with new data, which is nothing but 0x00 pattern. We use this API over here. So starting from this sector for 4 KB of data, we need to put 0x00 pattern. That's a simple thing, and again we put this into a while loop, redundant while loop, and then at the end we will come to the verification that each memory location has been set to 0x00. For that we use this API, and for this, since the default is flash 0 pattern, for using this definition we need to set the memory locations to 0x00. So that is the reason why we have set each memory location to this pattern. And at the end, once all this is done, we just protect the sector by using this API, and the loop comes out. And each time, and let's go back to the main program. So for each sector, when this is done, the erase, program and verify cycle is done, we increase the count and we move on to the next sector. Also we include this condition over here, which is nothing but our hardware reset or a hardware interrupt. So as soon as when we press the button, since we have defined it as a complement, so when we press it, it will set to 0, and till the time this is pressed, this will hold the program within this loop. And if that time exceeds 1 second, our watchdog timer will kick in, it will time out and it will reset the program. So this is nothing but our basic resetting and interrupt routine that we are using. The simple condition over here set by the switch, and this loop will complete the erase, program and verify of all 128 KB of locations of all 32 sectors. So once that is done, we will again reset the timer just in case it doesn't time out our system, and reset it. So to indicate the completion of the erase and program and verify cycle, we switch on the green LED. and this we can do simply by using this count over here. So while the count is going from 0 to 4, that is 5 times, we wait for 200 milliseconds, we reset the Watchdog timer just in case it doesn't time out, and we use this condition again over here. If we press it, or if we press the P1.4 button, it will reset the whole system. So that is nothing but that, and this loop creates a delay for 1 second, and our green LED will be on for 1 second, and then we switch off the green LED. Now it so happens that the erase program and verify cycle may not go till 1 minute, which is the case that I am facing right now. So we will see it in the demonstration again that time is much less than 1 minute. So what do we do in the remaining time from the end of the cycle till 1 minute? So what we do is that we can just put the board in idle condition by using this delay. This is a custom delay for my board, my program. It's taking this much delay to create 1 minute, to reach 1 minute basically, and in that 1 minute we put in the condition for the hardware reset, condition for resetting the timer, and we wait for 0.2 milliseconds multiplied by this factor, and it reaches the time of 1 minute, I'm sorry. So 1 minute is reached, and as soon as 1 minute is reached, we will switch on the blue LED given by the same logic that we discussed for the green LED, and then we switch it off, and this whole thing indicates that one complete cycle of erase, program and verify has been done, and then we start all over again into this from here. So this loop goes on continuing until unless a hardware reset is done or the Watchdog timer times out. So this is our basic function, the basic code, and let's see a small demonstration for the code. Okay, so let's see a small demonstration of the challenge. Here is the code that we have written, that we have already discussed in the previous section. So, and the board is connected. As you can see, it's not in the transmitting state, it's only receiving right now. So let's debug the code. The green light that you saw was from the previous cycle, so let's just ignore that. As you can see, a red light went on that indicated that the program is burnt onto the flash, and now we can see that the board is receiving as well as transmitting data from the CCS Studio. So what will happen is that as soon as I press resume over here, we'll see a red light go on at port 1.0, which is over here, which indicates the start of the program. And as soon as the flash memory erase, program and verify sequence is completed, we'll see a green light go on for 1 second at port 2.1, which is over here, which is the multicolor LED over there. And I've also programmed the code to indicate a blue LED go on after 1 minute for 1 second, which is at port 2.2 over here. So basically what's going to happen is as soon as I press resume, a red light will go on over here, and the board will erase all the 32 sectors, verify that all the sectors are deleted, each sector, one sector at a time, and then write the data sequence of 0x00 in every memory location for each sector, and this will go on for 32 sectors, which we discussed. It comes out to 128 KB of flash memory. So let's press resume, and we will also see that we have set this port 1.4 button over here as the reset, which will hold the program at a particular point, and since the program is held, we'll see the Watchdog timer come in and reset the whole program, so which will be indicated by a blinking red light over here, which we'll also see. And since I'm recording with my phone, I'll be using an online stopwatch, so it will take me like a second to switch over. So let's take that 1 second also into consideration, So here it goes. So red light followed by green light, and after 1 minute a blue light at 1 minute. Okay. Yep, here it goes. As you can see, we saw a red light. Let's take 2 seconds of delay. So let's see how much time it takes to erase the flash, program it, and verify the data for all the sectors. We'll wait for the green light, green LED. Yes, so we saw green LED at roughly 22 seconds. So let's take 2 seconds delay. So it took roughly 24 seconds for the board to erase all the memory locations and program them. So let's say we'll see a blue light at 58 seconds to indicate a new cycle, and as soon as a new cycle starts, we'll see one more demonstration for one more cycle. So I'll reset it at 58 seconds as soon as the blue LED comes on. Okay, that's roughly 58 seconds. Again, hopefully, again we'll see LED light at somewhere between 23 and 24 seconds. Yes, exactly 23 seconds. That's very good. And since it took me, let's say, a second to reset it, so again a blue light at 59 seconds this time. We'll verify all the memory locations in the next section on the on-screen camera or the on-screen recorder. This is just a demonstration for the board. So blue light at 58, 59, 59. Yes, that's pretty accurate. So, and we'll just demonstrate the reset button over here. Let's focus it on this. Okay, so as soon as I press this, we'll see the red LED go on over here, which indicates the Watchdog timer is resetting the system at every 250 millisecond cycle. And till the time I keep holding the button, the Watchdog timer will be resetting it. And as soon as I leave it, another cycle of flash memory erase, program, and verify will continue. Starts. So basically that was a challenge. Let's see the memory allocation and other memory features on the on-screen recorder. So let's look at the memory browser and check whether what is going on when our program is running. There's one thing I need to verify. In the previous screen, there was an error over here, which was basically a parameter which was I put it wrongly, so I've corrected that in this section. Okay, so let's debug this, and our board is connected right now, and let's debug it in real time and see what is happening within the memory location. So let's debug this. Okay, so we are ready to run the code. So what I'll do is we'll place a few breakpoints and see what is going on after every function is executed. So I basically want to check 4 functions: the erase verify, the program, and the program verify. So for the erase verify, I'll place a breakpoint over here. Then for the verify, I'll place it over here. Then for the program, I'll place it over here, and for the last verify, I'll place it over here. And we'll see that the program halts at every breakpoint, and we can see, and for the first iteration it will go for the first sector, which is the location I've already put in for the first sector, and we'll see what happens at that location. So initially what will happen, all the locations will be erased because I have run this code a few number of times. So but we'll see that whatever be the memory, whatever be the data stored in every location, they'll be reset to FFFF, So let's run the code and we'll see the program halt over at this point. Exactly what happened, and let's see the location. So every memory location starting from 20000 has been set to FFFF. So let's see if we are getting any error for the verify program. Okay, so that is also executed properly without any error. So now let's see. So what should happen right now is the program function should program the 4 kilobytes of data. So we should get a 0000 pattern from 20000 to 20FFF. So let's see if that is happening. Exactly what happened. Let's go back to this memory location. So it started, so the previous ones are FFFF, and starting from 2000 to 20FFF it should be 0. So that is exactly what is happening. And from the next memory location, that is 21, it is still FFFF. So this sector will be cleared in the next iteration, which we can again see. So let's verify if this verification function is working properly, and indeed it is. So let's go back to let's move on to the next sector. So as again we can see, we have again stopped it at the next sector erase, and let's see if this is verified. It is verified, and now all these memory locations starting from 21000 to 21FFF should be put to the 00 pattern, and indeed they did. So let's check that. Yes, till 21FFF it's been. So right now we have erased, verified, programmed, and again verified 2 sectors. So this will go on for all the 32 sectors. So let's remove the breakpoints and see what is happening in real time. We have removed the breakpoints, and again let's run this. So what's gonna happen is all memory locations will be set to 00 till 3FFFF. So let's see that. So let's put in 4 and see a memory location just before that, and they have been set to FFFF, and they'll be cleared. They'll be set to 000 shortly. See, so that was just after the green LED which I saw, which you can't see. So everything has been erased and set back to the 000 pattern. So that was basically our code, and what I want to do now is see what all optimizations can be done with this. So let's stop the code over here and go back to the edit section, and let's build the code. So basically the optimizations that we can do with this is reduce the data that the code uses, the power the code uses, the program uses basically, and include other APIs. So that is what the advice we'll get is to include the timers to reduce the power consumption and to reduce the coding that we have done, the data used by the code. So let's build this and we'll see the advice pop up. Yes. So that is exactly what we get is use insize types to reduce the code size, use a timer module to reduce the loops that we have used, use an interrupt and move it to the RAM, and then we should see another power. Yeah, so it also gives us a power advice. So these are the 4 things that we can optimize within this code, but since we are using our basic C code, so maybe for the next challenge we can use better APIs and reduce the power consumption, the size used by the okay, let me just show you one more thing, the size used by the code and the timers to decrease the number of loops that we have used. So initially I needed somewhere around 8,000 bytes of data to be programmed to the flash memory, but I have optimized the code a little bit, and now I'm just using 6680 bytes, so that is quite a bit of reduction. So eagerly waiting for the next challenge, and this is the end of the first challenge, and hope you've understood what I wanted to show you. Thank you.